the title towards predicting client benefit and contribution in federated learning from data imbalance. And the motivation of this work comes from the fact that federated learning as a paradigm that allows a cohort of clients to jointly train a machine learning model while maintaining data privacy is also known to suffer from data imbalance present at the different client sites. And also federated learning is known to have different benefits and contributions to the individual clients, and that this magnitude of benefit and contribution varies quite greatly in some settings. So in turn, clients willing to join a cohort in federated learning cannot predict if and to what extent their participation will be beneficial to them in terms of the performance achieved using the final model. And also cohorts cannot predict the value of each individual client willing to join the federated learning. So the current lack of determinants for benefit and contribution in federated learning motivates this work, and we seek to identify determinants that would allow to indicate the expected value of federated learning participation. So the goal is to first measure local data imbalance for each client while maintaining the data privacy, so taking somewhat of a data-centric approach here, and from this predicting the client benefit and contribution prior to the actual participation. The research question is, does pre-application measurement of data imbalance in federated learning environments allow to predict the benefit and contribution of those clients? We want to achieve those goals following the methodology I'm now going to present. So the first step is to actually measure data imbalance while maintaining data privacy of internet. To do so, we leverage a secure aggregation that allows to collect properties of mutually distrustful parties, or in our case, clients, as aggregates. And using secure aggregation, we compute the global label distribution. So the label distribution among all clients in the cohort, which we call capital V. So capital V contains information about the number of samples per label contained in the entire cohort, which we will then later need to know. And also from this capital V, we can compute the quantity of overall data in the cohort, capital N, by just summing all the individual numbers. And then we compute those three metrics: label imbalance, label distribution imbalance, and quantity imbalance. In contrast to the existing work, we compute those imbalances at the client level instead of at the cohort level. So we can assign each client an individual measure of data imbalance for each of these metrics. So label imbalance is then defined as the ratio of majority class size and the minority class size at client J. For label distribution imbalance, we require the initial computation of capital V to then measure the cosine distance of the local and the global label distribution imbalance. So in turn, label distribution imbalance captures the dissimilarity of those two label distributions. And lastly, we compute the quantity imbalance as the ratio of client quantity and the mean client quantity. So this spans between 0 and 1 for clients having fewer samples than the mean, and above 1 for those having more samples than the average. Thereafter, we measure benefit and contribution. To measure benefits, we take this local evaluation perspective into account. So instead of evaluating a federated learning model on a global test set, we evaluate it on each client's local test set instead. And we measure if and how much those clients profit from federated learning participation. This requires to also have a locally trained model for each client at hand, and then we define benefit of J, of client J, as the delta of F1 score achieved using the federated learning model on the respective private test data, and the F1 score achieved using a local model. And in J is greater 0, then the participation is beneficial for the respective client, and if not, it would be more beneficial to rely on the locally trained model instead. For contribution, the literature usually applies a leave one out analysis, so train federated learning model leaving out a single client at a time to then measure the actual contribution to the federated learning model. We instead propose to use a leave X out analysis, as it has two advantages. First, it reduces the computational expense, and second, it also, for large cohorts, allows the results to still remain significant. To do so, we cluster clients according to the measured imbalance. So we define this vector L containing all the three imbalances for each client, and then we perform a clustering on those clients. And then we iteratively leave out an entire cluster from training a federated learning model. And then we measure the contribution of the cluster similarly to the benefit as the delta of F1 scores achieved using the federated learning model and the federated learning model without cluster C. And again, if the contribution of C is greater 0, then the presence of the cluster increases the federated learning model's performance. Otherwise, it does not. And to then receive a contribution per client, we just divide their respective cluster contribution by the number of clients contained in the cluster. Lastly, for the methodology, we want to pairwisely rank those clients with accordance to both benefit and contribution. To do so, we form all unique pairs of clients per dataset we are applying this on, where we represent each client by their respective imbalances. So we get the feature representation of the clients J and K as their concatenation of data imbalances. And then we use a quite basic XGBoost classifier to perform a binary classification on which of those clients has the higher expected benefit, or for the other classifier, which one has the higher expected contribution. And then we perform this in two different settings. One, the intra-dataset prediction. So within a single dataset, we seek to predict those clients with the higher benefit or contribution to prove the general feasibility of our approach. And then later on, we perform the inter-dataset prediction to also show the potential of generalizing from individual datasets. Now to the experiments. We selected 6 datasets to do so that are known from literature and also differ in terms of domain, data quantity, learning goal, and input features. And then we perform federated learning using those datasets. Here we rely on federated averaging as a learning strategy. Although it is not the most sophisticated one, it's still one of the most frequently used ones. We set the number of rounds and local epochs with respect to the best performance on each of those datasets. And we also, this is worth mentioning, chose models of little complexity to demonstrate those effects. And then we distribute those data, applying first 80-20 split for train and test data. And then we distribute the train data among 50 artificial clients. And each time we do so, we enforce different magnitudes of data imbalance to simulate different magnitudes of data imbalance in those cohorts. And then we first show some findings with respect to the effects of data imbalance on benefit and contribution. And as you can see here, we plotted each client's imbalance measures and their correlation with benefit and contribution. For benefit, we find that all imbalances have a negative correlation with benefit, where the label distribution imbalance has the most severe negative correlation. For contribution, we show quite the opposite. So we see a positive correlation with all those imbalances and contribution, meaning that clients of higher imbalance are actually more valuable in terms of this contribution measure to cohorts of federated learning. Knowing those correlations exist, we then seek to train classifiers to tell us which of a pair of clients is the one expecting the higher benefit. Here you can see the results, one for the intra dataset prediction, for the intra and inter dataset predictions, both for benefit and contribution. And here at the top, we show that actually we can predict the client with the higher benefit quite to some extent. So for the best performance, we see a 0.89 accuracy on the covered type data sets, and with the poorest performance being 0.58 for CIFAR10. For contribution, we show that the best is on the diabetes data set with 0.67 and 76, and the worst being 0.49, so not even outperforming a random guessing approach. So we show the overall potential to learn from those data imbalances, but we also show some limitations. For the inter-data set prediction, we show similar results, yet a bit worse. This is unsurprising, as we show the potential to generalize from individual data sets. So we try to predict from different data sets here. To conclude, we showed that our approach is suitable to measure data imbalance in federated learning while maintaining data privacy of individual clients. And we also prove that the federated learning provides benefit to the majority of clients, but not to all. Further, we show that non-benefiting clients have a particularly high data imbalance, while vice versa, highly imbalanced clients also have a particularly high contribution. And lastly, and most importantly, we demonstrate the predictive potential of our metrics for benefit and contribution. There are some limitations to our current set of work, which are that we assume clients to be non-malicious. This would otherwise break, for example, the correlation we measured regarding contribution. And also we expect them to truthfully announce their imbalances. And as I pointed out earlier, the models of choice are rather simple. And for the future work, we consider capturing different or additional nuances of data imbalance, such as feature imbalance. And we also seek to find additional applications of data imbalance measurement and to further prove and improve the overall robustness of our approach. That was it for the presentation. Here are some references. Thank you for your attention.